All right, good morning, everybody. This is section 5 of chapter 10. We're going to go over some information about water. We're going to start this chapter just kind of talking about why water is weird, which is a topic that we've talked about in the past. And then we're going to end this section with some math on using those molar enthalpies that were discussed in previous sections, specifically related to water. And we're going to look at an example problem, and then I'm going to ask you to do your own problem. Now, remember that this is the kind of stuff we can ask on quizzes, so please make sure you are actually going through and paying attention and doing what I'm asking in each assignment. All right, so without further ado, let's continue with our structure of water. So one of the things I'm going to ask you to do on the next slide, in fact, is to go back and look at the structure of water. I want you to find a picture of it, and I want you to describe to me what this idea of water being polar means. And we discussed this last semester on how molecules being polar typically implies that they are asymmetrical. Water also contains hydrogen and oxygen atoms, and the presence of a hydrogen atom bound to an oxygen is what makes it possible for water to do this thing called hydrogen bonding. And that hydrogen bonding is one of those intermolecular forces that is very, very strong. And so when water is near other water molecules, it has a very strong attraction for those water molecules. It explains why water does what it does when it freezes. So why do the molecules still stick together, but why do they become less dense than they are when they're liquid? It explains why water has such a high level of surface tension and things of that nature. So this is just kind of like a general idea. The big reason why we think water is weird is because it's a small polar molecule that participates in hydrogen bonding. Additionally, we all know that when water is in its solid form of ice, that ice tends to float, and it's because when water freezes, and I want you to look up the structure of frozen water, what it does is it freezes in a hexagonal arrangement, and there is a picture of this hexagonal arrangement, if you don't want to use the internet, in your book on page 338. It's figure, in my book it says figure 5.2. I'm not really sure that that's correct, but it is, a good idea of what's happening with our water molecules when they freeze. And if you kind of look at the model of water, you'll see why they freeze that way. Which brings us to our first question. So make sure you're answering this, and this is what's going to get sent to me. You can go ahead and pause the video. If you need to go back, please do that. And when you're ready, you can go ahead and you can move on. Our next topic is just going to be a little bit further information on why water's structure makes it what it is. So again, when our ice molecules or our water molecules freeze themselves into place in a solid, what they do is they actually move themselves more farther apart or further apart than they do when they're in the liquid stage. And because they're moving a little bit further apart, they're actually creating more space between them, and it's allowing for that mass to be spread over a larger area, which means a less dense formation. So remember that we've talked about density, and density has to do with, I apologize for the noises, that's my computer's emails. But what that enables us to see is just that this idea of density is how many particles per unit area, and how heavy are those particles per unit area, right? If we have a lot of small, very heavy atoms in one tiny area, that's going to be very dense compared to something like water, which is going to have fewer molecules in that same area that don't weigh nearly as much as, say, something like a lead atom. Okay, so when we talk about liquid water versus ice, just remember that liquid water tends to be denser because the molecules can get right next to each other, and in ice they kind of spread apart when they freeze. Either way, when we're talking about the phase transitions of liquid to gas, that's our second topic on this slide. As our temperature gets closer and closer to it, we see that our liquid water molecules are going to have to absorb a bunch of energy in order to break up that really intense hydrogen bonding. Those hydrogen bonds are very, very important here. It's what makes water weird. It keeps those molecules close together. They don't want to break apart, so they have to absorb a lot of energy. This is another thing that just kind of leads into what we've been talking about. Water has a very unusually high specific heat, which is a topic we covered already this last week. What that means is it absorbs a lot more energy per gram than it would if it were any other substance. So water is a really good heat holder and a heat transmitter. So it has a lot of energy per unit area, but it also can give up that energy. It's why we use water to cook our food. It can actually input a lot of the boiling water inputs a lot of its energy into whatever the thing you're trying to cook is, and it changes the structure of those molecules by taking that energy and transferring it. And then from there, we can just kind of look at some basic structures. We've got liquid water on the left, solid water on the right. Ice is going to be a highly ordered solid, like most solids, like we talked about in our last section. And so when it becomes highly ordered, it actually has to spread its molecules out compared to when it's in that liquid phase. The next thing we're going to look at is the heating curve for water. And one of the things we talked about last section, section 4, I believe, was about phase transitions. So if we look at this graph, we're looking at temperature versus the energy being added. And a solid over here on the left, as you increase the heat of the solid, it's going to stay solid. It's going to stay solid. It's going to stay solid. And then eventually it's going to have to do this melting process. And right here is something I want to point out is this is a flat part of the curve. What does that actually mean? It means is as we are adding energy to this solid, we're not seeing it change phase. We're seeing it stay at that specific temperature. And remember yesterday we talked about it's going to stay at a constant temperature until all of the solid has become all of the next phase, so the liquid in this case. And in this particular flat part of the curve, we're going to focus on the heat of fusion. Same thing is going to happen in the transition from liquid to vapor. The molecules are going to stay at a constant temperature until all of the particles of one have become all of the particles of the other. If we were going the opposite direction, this would be called a heat of condensation. Same idea. It's just the opposite direction, which means the sign on the heat of vaporization gets flipped. So when I ask you this question on the next slide, you want to come back and you want to actually listen, we're going to stay constant because we're waiting for all of the molecules to change phase. And we have to be at the same temperature while that particular phase transition is occurring. Which brings us to our next question. So I'd like you to answer that in your notebook. Again, I just covered that. So if you weren't listening and you were just trying to skip right through, you might want to go back and listen to the last slide's information. And when you're done, go ahead and move on. All right. We don't have much left. This is a very short chapter. We're going to talk a little bit more about some of the physical properties of water. We've already said that when it's in its solid form, that ice is less dense than the liquid. And this is because of that more space being added in between the molecules like we saw. And this is the reason why it has a lower density. Fewer molecules per unit area means it's going to actually be less dense than liquid. And when something is less dense than something else, it tends to float. Good examples are like wood and water, etc., etc. We know that other properties of water, because we live with it every day, it tends to be transparent, it has no odor, it has no taste, it is specifically colorless unless you put it in something that has a color and then it refracts light. But for us, it is actually colorless. When we see colored water, so when we see green or we see blue water out in nature, what we're actually seeing is the reflection of light from an object through the water. So for instance, algae. If you guys have been paying attention to what's been going on in nature since everybody's in quarantine, one of the things that's happening in Italy is the algae that typically colors the canals in Venice that is green is actually settling to the bottom of the canals because nobody's actually going out and transporting themselves via the canal method like they usually do. So they're seeing the algae settle out, which means the water is actually transparent. It hasn't been transparent in years. So it's been a very interesting consequence of what's been going on lately. So just kind of, pay attention to what's going on around you. You get to see some pretty cool science as you're growing. That being said, we can talk about the molar enthalpies of fusion and of vaporization. And we will talk about both of those when we do our problem here in a second. But the molar enthalpy of fusion of ice is going to be pretty big. And we talked about why, because water is really good at holding on to energy, and water actually absorbs a lot of energy. So when it has to go from one phase to another, it's going to require a pretty big energy input, either when it's ice going to liquid or when it's liquid going to vapor. So we will see how that gets impacted by what we're going to look at here in a second. So the next thing we're going to talk about is the boiling point in molar enthalpy. So again, when we're talking about the enthalpy of vaporization, also going to be pretty high compared to other substances for a lot of reasons, but I mean, for instance, what we're talking about here all has to do with the fact that water is very odd. We're going to see that those values get really, really high as far as the molar enthalpy of vaporization because the bonds between liquid molecules are very, very strong. Remember, it's that hydrogen bonding. In order to get our liquid molecules to break apart from each other, we have to break those hydrogen bonds, which is going to require a lot of energy. So when that happens, the gas form of water, so steam, is going to have some of the largest amounts of energy per molecule than over other types of substances. So just kind of keep in mind when we do that. All right, so now we're going to walk through a sample or a sample problem. And this is actually in your book. This specific example is on page 339. So this is in section 5. And one of the question that we're asked is, how much energy is going to be absorbed when 47 grams of ice is going to melt at standard temperature and pressure? Now I'm going to remind you, what are standard temperature and pressure? If you remember from last chapter, standard temperature is 0 degrees Celsius and pressure is 1 atmosphere. So that's the first part of the question. The second part of the question says, how much energy is absorbed when the same mass of liquid water boils? So this is actually 2 steps of a problem. The first problem says, how much energy are we going to actually need to absorb in order to go from the ice stage to a liquid? And then the next stage is going to be, how much energy do we need when we want to go from liquid up to boiling? So 0 degrees up to 100 degrees Celsius. So first things first, we're going to go through and we're going to get our information. The mass of water when it's solid is going to be the same as the mass of water when it's liquid. It's just in a different form. So we have our 2 phases and their masses. We also have the molar enthalpy of fusion of ice and the molar enthalpy of vaporization. These are constants. These will never change if we're always talking about water, which is what the sample solution is going to have for you here in a second. And what we're going to see in a second is what are we trying to actually solve? And the first one is that we want to know the energy absorbed when the ice is melting, so when we're going from the solid to the liquid, and we want to know how much energy is going to be absorbed when our liquid becomes steam. So in order to do this, we're going to convert the mass of our water from grams to moles because we're talking about a molar enthalpy. This unit has kilojoules per mole. We're probably going to try and get rid of that number of moles or that mole unit because energy, which is the unit we're going for, is in terms of kilojoules. So we're going to convert our mass of 47 grams to moles, and we're going to use this number of moles for both the mass in solid and the mass in liquid. Just because it changes phase doesn't mean it weighs anything different. If you aren't sure where this 18.02 grams per 1 mole came from, I will remind you to look at a periodic table. This is a formula mass. This is a molar mass. That's all it is. All right, so the next approach is going to be to use that molar enthalpy of fusion, and we're going to multiply that times the amount of moles of the substance we have. That'll give us a unit of energy. That'll cancel out our units, if you will. And what we're going to see is when we multiply those things, we're going to get this amount of kilojoules when something melts. The next one, we're going to do the same thing for vaporization. We're just going to take the molar enthalpy of vaporization and we're going to multiply that number of moles. Because all we're looking at is how much energy is being released on the actual transition. We're not looking to actually figure out how much heat is being generated when we go from 20 degrees to 50 degrees, which we could use Q equals MC delta T. Hint, hint from last week's from last week's specific heat homework set. That's a little different. For this, we're just looking at how much energy do we need to do the phase transition itself? How much do we need to put into our ice to melt it? How much do we need to put into our liquid to boil it? And here is your question. I want to know how much energy do you need to melt ice at 0 degrees Celsius. So you have to pick which one to use, the molar enthalpy of fusion or the molar enthalpy of vaporization. Hint, hint, we are not boiling, so this is not vaporizing. Use that, show your work, and then turn that in. And that is the end of Chapter 10's lectures.